Yeah, we really use it for anything. Can we just grab whatever calculator? Even if we have a graphing calculator, why is that gonna help?
All right, guys, let's get started. We have to review 3 chapters. There's a lot of things to review. So, and just for this week, for the makeup labs, if you can attend one of the sessions, I mean, for those who are attending the makeup labs, if you cannot attend like tomorrow and you were assigned tomorrow, you can do it tonight. But it's just for the makeup lab week because we have more space, so we can play around with the students. But as of next week, I'll post the next pre-lab after your midterm. So as of next week, things will get back to its normal routine. It's just as usual. Yeah. No, it would be like 1 hour and a half for your test. Yeah. Okay. So let's get started. On the chapter 1, if you recall, I'm sure you recall now, we were talking about the different metrics to come up with the performance, like quantifying the performance of a processor. So that was in an abstract form, we were talking about the clock cycles, right, as the multiplication of instruction count by the number of cycles per instructions. Okay? And just like that, we could have computed the CPU time as the multiplication of instruction counts, ICs, and the clock per instructions, CPI, and clock cycle time, right? And that would be equal to your instruction count multiplied CPI divided by the rate of your clock for the processor. And we were talking about different factors that can, vary these numbers in each level of programming paradigm. If it's on at the architectural level, compiler level, high-level application level, and so on and so forth. So using this, we could have had the big picture as the CPU time equal to the fraction of instructions with respect to program, multiply clock cycles with respect to instruction, multiply seconds divided by clock cycle. Okay. Again, as a big picture, we talked about the different factors that algorithms, programming languages, compilers, and architecture can play around with these specific numbers. All right, so let's just have a small question to review this. So question 1.6 in your book is actually saying consider 2 different implementations of the same instruction set architecture. So the instructions can be divided into 4 classes according to their CPI. Okay, so we have 4 classes of instructions, A up to D, and we have 2 processors, one with a clock rate of 2.5 and a CPI of 1, 2, 3, and 3. So one is for the first class, one is for the first class, up to 3 is for the last class. Okay. Just like that, you have another processor, P2, with a clock rate of 3 gigahertz and a CPI of 2, 2, 2, and 2. So now the question is, given a program with a dynamic instruction count of 1 exponential of 6, so 10 to the raise of 6, and those instructions have been divided into classes. 10% of these instructions are divided into class A, 20% of these million instructions are divided into class B, half of those are into class C, and the remaining 20%, what is it? The remaining 20% is in class D, okay? So the question was, which processor is faster, P1 or P2? What is the global CPI for each implementation? And B, find the clock cycles required in both cases, okay? So it's pretty easy to tackle this. They're just simple formulas. So the first one, for the class A, you recall we had this as overall instruction count, so we can divide it into different classes. 10% for A, 20% for B, 50% C, and 20% D, right? So each class has, so for instance, 10% of 10 to the raise of 6 would be 10 to the raise of 5. We have 20% of those, so double the size of this, 5 times the size of A, and double the size of A again. So these are the different instructions grouped into different classes, okay? So you can simply find the total time for P1 and total time for P2 using the ones that were given already. So you needed only number instructions, multiply CPI divided by the clock rate, just like what you had here as your CPU time, okay? So it's a simple math. No fancy calculators needed, even here. And then you'll come up with a number 10.4 multiply 10 to the raise of -4 second. And the other one is a little bit higher, okay? 6.66. So easily, when you have the time, the total time for the processors, you can find the CPI, right? It's just a matter of multiplying this number to 2.5 and 3, and what is that, 10 to the raise of 9? Yeah, that's because of the gigahertz. So you're going to have two CPIs, one for P1, one for P2. CPI P1 is 2.6, CPI P2 is 2. So which is faster? So why first? Why second?
It has fewer clock cycles.
So what does CPI mean? Let's start from this.
Clock cycles.
Clock
cycles per instruction.
So what is it?
Clock cycle per instruction.
Is it clock per instructions or cycle per instructions?
Cycle.
So the lower the better or the higher the better?
Lower the better.
So somebody Google's CPI for me. And write computer architecture in front of that, yeah. If it's referring to time, perhaps it's not referring to time. Is it? You have midterm in 2 days. What is CPI? Now I'm worried. Lower is the better? So C is clock or cycle? So cycle, can anyone intuitively define what is a CPI?
How many times goes for us for everything to figure it out in the end?
Per instruction?
Is it like how many cycles they run, the CPU runs? For each instruction?
It's per instruction.
Yeah, so for each instruction, how many times the CPU runs? Like the whole cycle?
50%. Right.
Would it be like how many cycles it needs to run like to do one instruction, to do one task? So like if one of the lower be like the better choice because it doesn't have to run that many cycles to do one instruction.
But does it depend on like the clock rate? Because sometimes it's faster, some CPU runs faster, sometimes it runs slower.
Yeah? It should depend on that.
With the formula for CPU time, the height, the lower the CPI, the lesser will be the execution time, so the faster.
Great.
We don't have to calculate the time to get the global CPI, because we can just multiply the get the average CPI for each processor by multiplying the individual CPI times the percentage, so 0.1 times, and we get the same result.
Yeah, that's right. So, for B, we have to find the clock cycles required in both cases. So you see, if you just use that formula to find a clock cycle for P1 and P2, you're going to see that the final result would be 26 multiplied 10 to the raise of 5, and on P2, it would require 20 multiplied 10 to the raise of 5. Thus, P2 is faster because it requires lower clock cycles to accomplish the same task. Okay? So there can be a variety of questions asked from these two formulas and other things. All right, let's go to chapter 2. So for chapter 2, we've been talking about different ISAs, different instructions, and how we're going to write down some small segments of code in assembly depending on the type of the code that we were asked. If it was a conditional statement, if it was using a stack, if it was using a leaf procedure or not. So depending on that, we have different variety of tasks. So as a quick review on this, you recall that when we are dealing with if statements, we are actually deciding between two cases normally. On this case, we are checking a condition if I is equal to j, if it was equal or if it wasn't. So we're going to have two different routes. Okay, you had this already in your chapter 2 book. So for the compilation, when we have the assembly code in RISC-V, so that branch not equal will do the job for us, assuming that we are using these registers X19, 20, and so on and so forth for F and G. Okay, so the result of this is going to decide either we're going to go to the else section, annotated here, or we're going to continue going down the path one by one in the instructions we have. And at the end, if you want to exit, so in this example, we have an exit point, because no matter what condition brought you here, you're gonna exit here, and that's why we call it unconditional, because it doesn't matter. At this point, it doesn't matter in any condition you're gonna exit this pass. That's why this branch equal x0 is always x0, so definitely you're gonna exit here. Okay, you're gonna jump over this line. Is it clear up to now? So the other notation that we were talking about was using a stack. So depending on the number of, so a stack was part of your memory. You could have used it, and it's available to the programmer to take use of that. It's last come, first serve. So the notation of a stack was that the address starts from the higher addresses up to the low address, okay? And there is this pointer, we call this SP, which is a stack pointer. So by the number of registers that you are pushing into a stack, you're gonna have to adjust this SP in order to use it when you pop things from the stack. So if you use 3 registers, you have to make sure that you're pointing to the right one, and after popping, it's gonna be back up automatically. So as an example that we talked in the class, we were asked to implement a small addition and subtraction using stack. So since we were dealing with 3 variables, so 3 registers in a stack, we had to adjust the stack pointer by 3, which is minus 24. Each of those are 8. And then you were starting to st each of those. We do the add. G plus h will be saved in x5. I plus j would be saved in x6. And the final result would be the subtraction of these two, x5 minus x6, right? And then finally, we're going to do this restore from the stack. So that's why these LDs are the opposite of the STs here, from the address 0, 8, and 16. Finally, you're going to return to the caller. You recall that we had a jump JAL and JLR, so you would have used somewhere before this code we had already a JAL, and we are just returning to that address. That's why we call it return to the caller. So it's going to go to the 0 address of the X1 because X1 was the address that we were sent from. Okay? So everywhere when you use JAL at the end, when you want to come back, you're going to use JALR. Any questions so far? So let's see. Let's have 2 questions to review. The first one is 225. So the question is, translate the following C code to RISC-V assembly code. Use a minimum number of instructions. Assume that the values of A, B, I, and J are in register X5, 6, 7, and 29, respectively. And also assume that register X10 holds the base address of the array D. Okay? So we have 2 loops, nested loops, I loop and the J loop, and we're going to have some arithmetic with and some updates with the array D. Okay? So 4 multiply J would be the address of multiply J of D would be updated by I plus J. Okay? So let's see the answer and let's review that. So that's the code. I put it here. The C code. So first let's start from the I loop that corresponds, the iterator of the loop is I, this one, and that's for the J loop. Okay. So first we have to initialize it, I equal to 0. Then we're gonna check for the condition that while I was smaller than A, we're gonna do the following, otherwise we're gonna jump to end I, right, which is the end of the loop. 2 other add I, pretty simple. Then we're gonna enter the second loop, which was the nested loop. The second one did the J loop. First of all, we have to again check for the termination of the loop. If that was the case, we're gonna be out. Again here. Then you have to compute this and store it in X31. So add X31, X7, and X29, which hold this I and J. And then since we were told that, let me see, the register X10 holds the base address of D. Let me see, yeah, here. So now we can update the 4 multiply J's address of D by the result of x31, and x31 contain the value of I plus j. Okay, so we use these results to store it to the address of 4 multiplied j of d, and finally, after that, we're gonna do the j plus plus because we need to iterate over the loop, and then this is the jump and link. So that decides either we're gonna go to the loop j. That means either we're gonna come back to this loop or not. If that wasn't the case, we are outside this, and then that's the last iterator, I plus plus, and then definitely after some iteration we're gonna be out. Okay, we're gonna go to end. Questions? Yeah.
So BGE isn't that greater or equal? But doesn't that mean it runs on extra loop?
Why this?
Because x7 start is I, right? So it starts from 0. And then when x7 is equal to a, it doesn't end the loop. It'll keep going another loop. So that means the end result will have one extra loop.
It's BGP stuff. It's greater than or equal.
Yeah, so does that mean even when it's...
As soon as
Oh, I
it's
see.
equal.
Okay.
Why are we not shifting J by 8?
Shifting j. Why do you have to do that?
Because of like indexing in the array, you have an index of J, you have to SLI by 3 or shift by 8.
So if you shift j by 8, I mean, are you talking about an alternative solution to this, or?
No. I'm asking why are we not doing that? So like in all other problems, we had to, whenever you have an index that's given as like I or J, you have to multiply it by 8 or check it by 3, it doesn't matter, to be able to access it.
Like the 4 times J, like we didn't like we didn't multiply J by 4 anyway.
Or you just keep adding 32. That's not. You keep going. You just keep adding 32 every time.
Oh, I see.
Do you see why? I mean, definitely there are alternative answers to this because it's programming. You can do it many ways.
I didn't understand that. Could you explain why?
Can you explain to your, so everyone understands?
They added 32, which is multiple, is like 4 times 8, and
Oh, I see. Okay. Thank you.
Sorry, what if in the exam we write an alternative?
That's okay. Yeah.
How are you gonna check this correct?
We can read it and then we'll understand if you got the solution or not. I mean, I'm not gonna ask you to write like 200 lines of code so that we have 200 different ways to write that code. It would be very small segments.
Well, usually, the sample question they ask us to write the minimum lines, but what
Yes.
if we write more than the
I'm not gonna be very picky on that unless you just, instead of writing 4 lines, you have written 12 lines. Other than that, yeah, it should be fine. Questions started. Yeah.
Sorry. For the top part, you initialize like the loop for I, right? But how come you don't do the same for J?
Say that again.
You know how it says initialize I equals 0, right?
Mm-hmm.
For one of the comments, how come you didn't do the same for the J?
Oh yes, that's right. Yeah, we should have done that.
Do we have to do that?
I mean,
they're always to 0, right? When this
Yeah.
is off.
Yeah, you're right. I mean, it should have been.
There should be something.
Yeah. It's a minimal, like sort of a pseudo version of that. So yeah. What is it?
Oh, okay.
Oh yeah,
What would you do in the next project?
it's on the 4th line. Yeah, I didn't see it.
But do we need to initialize it every time? Or
What is it?
do we need to initialize every time? Or doesn't it just automatically start from 0?
No, if the C code has, yeah, you need to
Do we
translate.
need to?
Yeah,
Okay.
yeah, yeah. Yeah, it was on the fourth line.
On the test, if we write that, and one of the lines from that is wrong, if I have to write a line, do we get a 0 for the whole question?
If everything was correct and you just missed one line, and that line was it was shown that it was a typo, and you understood, because if you write the rest of the things and you don't initialize J, it shows that you just you messed a little bit, but you had the idea, right?
And how
Yeah.
many of those questions are going to be on
What is it?
How many of those questions are going to be on the
Limited. Yeah, limited number of questions. Questions? Yeah.
So for the third line, you're storing you're storing the array at x30, right?
Yep.
What's the x10 representing?
So based on the question, it was mentioned that assuming that the register x10 holds the base address of array D. Yeah. So he's storing it by reference. Okay, is it clear? Okay, so let's have a look at another question 229. You had a similar question in your lab, I recall. So implement the following C code in RISC-V assembly. Remember that the stack pointer must remain aligned on a multiply of 16. Okay, so that's the Fibonacci sequence. And we're using the stack. Okay. So that's the code on top right. Again, just like the previous example. So we have, first we're going to check if n was 0. If it was 0, so we're done. We're out here. Otherwise, we're going to add I, x5, x10, and 1. Okay, and then we now check for this one, the second f. Again, if it was 1, we're done. So we're here. So now, this minus 16 is because we are allocating 2 words. Each of those were 8. So we bring down this SP by minus 16. Okay. Just like the examples we had before, so we have to ST those, save the return address for the 0th one on x2 and the 8th one on x2. Then here, we have to assign n minus 1 to x10. Let me see if it was, yeah. And then that's the jump. We're going to jump to the fib annotation and save the address in x1, okay? So that when JLR want to come back to the color, it knows the x1 address, okay? So then after passing this, we have to load the old one, which was the 8th address of x2, right, to x5. And then we ST that. Here you have this plus this value, okay? So, can anyone explain why we have another JL here?
It's recursive.
Yeah, because we are returning.
It's asking for fib n minus 1 plus fib n minus 2, so we need to do 2 times in order to get the one time.
Okay. Yeah. So this one will call fib n minus 1. This one will call fib n minus 2. Yeah, you do the same thing, load and store again, and then the final add would add the result of these two, okay, in x10. You load the save return address, and then you pop the two, you bring back the SP up 16. And finally, that's your done case. You're gonna come back or just you exit the routine. Questions? Yeah.
So if you have a question like this on a midterm, will you be using C? Like writing a subletter from this code up in C?
Could be possible, yeah.
Okay.
You're not familiar with C? I mean, it wouldn't be that different from, Java, right?
Yeah.
I mean, these 5 lines, I don't think it would be that much different in Java. Would it be?
Only slightly.
Like, yeah. I make sure I give you something that is completely equal to Java. Yeah. But again, I'm not going to ask you to write codes in the exam. I just want to make sure that you understand the process. Right? What is it?
We're not writing that?
No, you're writing the code. You're writing a code, but the purpose of asking you to write a code is not just to write a code, just like a developer. It would be minimal. Okay?
It's not gonna be this.
It's not gonna be that long, right?
Is it long?
That's quite long. To be honest, I can't do that that long.
Is it the same level as the difficulty as this or the one before?
I like your creativity in asking questions. Yeah.
What's the question?
We're trying to downsize the solution space. Yeah.
Would you accept the comments, so the pseudocode as the answer? Because that still demonstrates the logic.
That's true. Yeah. Can we do that?
What is it? Yeah,
We
it
can
says.
just do the pseudocode to demonstrate our logic.
Probably even harder.
I mean, if you write those comments, you've had the answer already,
Yeah.
right?
Alright.
If you come up with that code and don't write the equivalent on the left side, I mean, yeah, it's a miss. Because you did the wrong, harder part. You analyze the process, you write it down, and you can just,
So say I do something wrong with this. What's the tolerance for it? Like say I load something into the stack improperly. Like how badly would that destroy my grid?
It depends on we're not just gonna look for a copy paste of the results, right? We read through your solution and then analyze what effort has been put and what it shows about your ability to understand a question, right? So don't try to write garbage, okay? You have a space, you have your 8 sheet with yourself. Just don't just make random things. It would make our job harder. All right? It's not a history exam. I'd rather see I don't know something than to just parse 200 lines and see that was garbage. Okay? Please don't do that. Okay. Any other questions? All right. So let's cover a question from chapter 3. So we were talking about the floating point format in IEEE, and it supports multiple versions from half precision, single, double, and so on and so forth. So we were talking about the single and double. How we're going to represent scientific numbers, right? What's going to be the exponent? What would be the size of exponent in each of those single and double, which is 8 and 11, and the fraction size for single and double. So as an example, and also for the single, we had the bias of 127, and for double, it was 1023. Okay. So as an example, let's talk about the floating point multiplication. That was the flow chart. So you start by adding the bias exponent of the two numbers. You multiply the significance You normalize the product. You check if it's underflow or overflow. And then you round, normalize if needed, and then you set the sign. If the signs were not for multiplication, if one of them was negative, one was positive, so the output would be negative, obviously. So you just have to follow the process like that in this figure. I believe it was figure 3.17 in your book. So for instance, let's just review this again. You were asked to multiply two values in base 2, 1.000 of 2 multiplied to the raise of minus 1 by 1 minus 1.110 to the base of 2 multiplied to the raise of minus 2. Okay, so following that flowchart, you see that first we have to add the exponents without bias. So you have a minus 2 and a minus 1 here. Okay, so you're going to come up with minus 3 here. Okay, and then you use the bias representation. So it was a single precision. It was 127. So your minus 3 plus that would be 124. So up to now you completed the first stage, the step 1. Then what you need to do is to multiply the significance. Okay. You remember that the step was as followed. So the first one, you check from right to left. If the first one was 0, so you had a 0 line to the size of you had in both of the significance. So now we have 4 zeros because this one was 0. You shifted again right. You are having this 1 over here. So the 1 copies the same amount of the first one. So at this point you have 1,000 because this was 1. So you have a copy of this here. You shift right again. So now you're talking about this guy here, this one. Another copy of above, which is 1,000. Another shift, you have another 1. So you need to have another copy of this. Okay? That's another 1,000 here. So you add them up, you're going to end up having a value 111,000 in base of 2. Okay? You were asked to keep the bits up to 4. So the output won't be this long. It would be only, you have to change the representation to 1.110 multiplied to the raise of minus 3. Okay? To make sure that it's 4 bits. So now you enter step 3. Now we have to check the product to make it normalize, and also check if it's within the underflow or overflow range. Since it was minus 3, definitely it's within the acceptable range of being okay. So it's not an overflow, neither underflow. Okay. So we can pass step 3. Under step 4, we just have to round the product. It was already rounded, so we don't have to do anything about it. So the same comes down here. And also, the final step, you are multiplying a negative to a positive. So you have to adjust the sign of the output of the product. So 1 was negative, so the output would be negative. And finally, you can convert it to decimal if you were asked, right? If not, you can just leave it as follows. Okay? I'm sure this was pretty easy, right? Okay. Any questions? Yeah.
What happens if when we multiply, like this is pretty simple, but there's problems we have like a column full of ones. How do you carry